All right. So today, this is the second part of 3 videos. I want to explain how to do we're going to do some free multiple choice and a little bit of short answer questions, just to kind of practice these hypothesis tests for two proportions ideas. So here is a free multiple kind of question part from your notes. Here we go. In an experiment to learn whether substance M can restore memory, the brains of 20 rats were treated to damage their memories. First, the rats were trained to run a maze. And after a day, 10 rats, which were determined at random, were given the substance M, and 7 of them succeeded in the maze. Only 2 of the 10 control rats were successful. Okay, now when I look at this, I definitely have 2 groups, and we are talking about a categorical variable here. We're talking about whether or not they succeeded or not, so we have counts. However, we have this, this is definitely an experiment because we don't have rats from Avon and rats from Brownsburg, and we sampled from those 2 groups. We just have like a group of rats, and then we're going to take that group of rats, that one group, and we're going to split it into 2 treatments. So we are the ones that decide what gets which treatment. That makes it an experiment. Okay, so the questions sample z-test for the difference in true proportions, and then I have some answers here like gives a z-score and a p-value, and then I have some others that say should not be used because, and it seems like we're talking about some conditions. So I could maybe check those first 3 by running this 2 proportion z-test in my calculator, and it's really tempting, but remember, you really shouldn't do that unless you check your conditions first. So your conditions for inference are random, 10%, and approximately normal. So random. Now this is an experiment, so we're going to check, is there random assignment to treatments? And there is. Okay, random assignment to treatments. It says they were determined at random, so that part is good to go. Okay, now the 10% condition, I don't have to check here because we use the 10% condition when we are sampling without replacement. We are not sampling without replacement. We are taking a group of volunteer rats, and we are separating them into 2 groups using random assignment. So if you don't have random sampling from 2 different groups, you don't have to check this 10% condition, because if you're not sampling, you can't be sampling without replacement. Okay, so you don't have to check that condition in this problem. Now, in the future, you might have to check that. So don't be like, oh, we never have to check that for this. That's not true. It's only when you are taking samples. Okay, so that's not an issue here. And so the other one is that large counts condition. So remember, what you have to do to check this is for both groups, you need to check that n times p is greater than or equal to 10. And that n times 1 minus p is greater than or equal to 10. And we would need to do our best check of that possible. Now, the problem with this is that if we are doing a 2-sample z-test, then we would be assuming from the start that p1 would be equal to p2 in our null hypothesis. So we would have to check our expected counts using that special p hat combined. Okay, so that would be, in our case, let's see, we've got 7 rats out of the first group and 2 rats out of the second group that were selected, and then we've got 10 plus 10 right here. All right, so that is going to give me a 9 out of 20 with 0.045. All right, so we have 5.5% here. Now, the issue with this is that when I go to check n times p, both of these sample, or not really sample counts, but both of these sample sizes, I guess most of these group sizes, are 10. So there's no way that I can take 4.5% of 10 and get greater than or equal to 10. So that definitely is going to fail. So we should not use this as it stands because we've failed that condition. And the reason why is because this isn't approximately normal then. Maybe it's skewed, maybe it's non-normal, who knows. But this sampling distribution is not well modeled by a normal distribution. So there wouldn't be any point in finding a z-score and using that to find probability, because unless you got a normal distribution, I mean, you can find z-scores all day long, but that doesn't mean that that probability with it would be any good. Okay, because if the shape's not normal, then the probability coming from that is just like garbage. Okay, so the next one says, assume that the experiment is repeated this time and all the conditions for inference are met. Okay. All right, so these are conditions are met. Okay, we check our large counts. That doesn't work out. Okay, so assume all the conditions or inference are met. What would the conclusion of the hypothesis test be? Okay, so that conclusion means that what we really want to do is we want to run this test in our calculator. We're going to assume all the conditions are good, and we need to find the p-value for this, and we need to find the test statistics. So what you want to do is identify these pieces. So according to this particular scenario, we've got 35 out of 50 of the mice who were treated with substance M, which sounds like something that you would give someone in a beginning of a superhero movie, right? Okay, substance M to improve their memory, and the other control group we had 28 out of 50 who were successful at that maze. So there's our observed counts for those, observed counts and our observed totals. And we're going to use our nspire to run this 2-sample z-test with an alternate hypothesis here that PM is greater than PC. Basically what we would say is for this experiment, the substance M is more effective at helping these rats successfully navigate this maze after their memories have been damaged. All right, so to get to that 2 proportion z-test, you're going to go menu, okay, and statistics and stat tests. Okay, so if you are at home, you're going to want to pause your video here, and you're going to want to pick up your calculator and run these tests along with this. Make sure you can get these numbers, okay? So menu, statistics, and stat tests just from a scratchpad screen, and you're going to get to number 6, which is the 2 proportion z-test. We're going to enter all these numbers. There is a drop-down menu, just like our confidence intervals before, which is going to allow us to pick greater than, P1 is greater than P2. Okay, now we get this result from here. We end up with a z-score and a p, and when we're talking about phantoms, our acronym, that's the T and the O, the test statistic, and obtain the p-value. Notice p-hat 1, that's what you get if you do 35 out of 50. P-hat 2 is what you would do if you got 28 out of 50. And then p-hat here, that would be, now we didn't have to find this earlier to check, but that's p-hat combined. That's what we would have to do to check the expected counts. And to do this z-score by hand using the standard error formula if needed, that's the what you get when you take all of the expected counts out of the grand total. So it's kind of like a weighted average p-hat, sort of, okay? So our z-score is 1.449, which doesn't seem too far away from the mean, and we end up with a p-value of 7%. Now, in this case, it does not give us the alpha value in the problem, probably because I forgot to write it there. But if you're not given an alpha, it's up to you to write one down. You just can't say alpha. You have to tell what it is. So you can either say somewhere in your problem, assume alpha's 5%, assume alpha's 1%. Doesn't make a big difference in this problem because 7% is bigger than both. But you can also write it something like this. Since the p-value is greater than alpha, 0.05, we fail to reject the null hypothesis. Okay, p-value is greater than alpha, fail to reject. This is not unusual enough for us to think that this couldn't have just happened by chance. Like, yeah, our sample statistics are showing us that the M group did better, okay, for the sample, but maybe that just happened by chance, okay? This could have just happened. So I'm not convinced that the proportion of mice in the treatment group that would succeed is greater than the control group. Now, I want to be careful about this because after I did this, I kind of disagreed with myself a little bit. I want to make sure that we are referring to a bigger picture than what we actually have. So I'm going to fix this and I'm going to say the true proportion of mice given the treatment, and instead of saying given the treatment group, because like if we were to do this with more mice, so the ones in the treatment group, that's p-hat, that's the 35 out of 50, which I know is larger, that would succeed is greater than the control. And then I'm going to refer to this, I'm going to say for rats like these, or like those in the study. Okay, I just want to be a little bit more careful here and make sure it's very clear that I am not talking about my sample, or sorry, my treatment group exactly. I am talking about this experiment as a whole, okay? And I can't say like for all rats because we didn't randomly sample these rats, okay? All right, now what potential error could you possibly be making? So remember we said fail to reject. So fail to goes with type 2, fail to type 2. So we failed to reject the null hypothesis. So we could possibly be making a type 2 error. So it would be a mistake to fail to reject the hypothesis if it was false. So if the null hypothesis is false, and actually what's true is if that substance M is more effective at improving memory. Okay. All right, let's look at this next one. It says a survey interviews 500 female college students and 500 male college students. Researchers want to determine lost my picture here. Researchers want to determine whether or not there is a difference in the proportion of male and female college students who worked for pay last summer. In all, 410 of the females and 484 of the males say that they worked for pay last summer. Now, we did this problem yesterday in the notes, but we did a confidence interval, I think, to estimate this true probability. Okay, and so it says, let PM and PF be the proportions of all college males and females who worked last summer. All right, so as we're looking at this question, this is a multiple choice question. And so the first thing you always want to look for in multiple choice questions is there anything that can I get rid of because it's the wrong format? So we talked about that yesterday with confidence intervals and with like the standard error equation, making sure the standard error equation is really just literally the right format, like big square root number times number divided by number plus number times number divided by number. So same thing here. Are there any of these hypotheses that we could get rid of simply by they're the wrong format? And if I look, remember that we always want the null hypothesis to be a statement of equality, okay? We do have a couple of those that we could get rid of. Those are definitely the wrong format here. So the ones that have a greater than or not equal to, that's not the correct kind of hypothesis that we do in AP Stat. So we don't want that. So I'm going to get rid of those right away. And I'll look at the other ones. The other ones all seem to be okay. All of the null hypotheses are equals, and all of the alternate hypotheses are inequality statements, which is good. But we need to find the inequality word. So you want to scan through the problem. Where's the inequality word? I'm looking for like less than, greater than, different, the same, something like that. And the only kind of phrase that we see is this idea that there is a difference. There is a difference. So that must mean that we're going to test that they're just literally different. That's that not equal to. All right, so that's going to be our null hypothesis. Now, the second questions here says that the researchers report that results were statistically significant at the 1% level. Statistically significant at the 1% level. And I'm just going to pause here really quick because before you could do this, they would have to check the assumptions. So in the last example, we talked about, is it random assignment to treatments? In this example, we would look at this and say, do I have two independent random samples? And we do, okay? We have two random samples here, okay? And since we're sampling, we would also want to check the 10% condition. We don't know how many people are at this college, but we'd need to check, is it reasonable that 500 is less than 10% of all female college students at this university? Seems reasonable. That'd be about 5,000 females, would make sense. And 550 less than 10% of all male students at this university. And again, that's 5,500. We probably are good to go there as well. So if this is a fairly large university, we should be good on that condition. The other thing we would want to check is that the expected counts on this would yield a result that were bigger than 10. So our sample size is fairly large, 500 and 550, which helps, but we'd have to check that against that p hat combined. So we would want to take that 410 and that 484 and take them out of 500 plus 550, figure out what that is, and check those expected counts with both sample sizes to see if it works. Okay, so we're going to assume the researchers did that. Okay, so it says statistically significant at the 1% level. Now, if you've got your notes packet in front of you, I want you to highlight, underline, do something to draw attention to this phrase right here, statistically significant at that 1% level. Okay, basically, anytime we say something is statistically significant, we mean that the probability is really small of this happening by chance. Okay, we don't think this happened by chance alone. This result has a really small chance. It's significant. It makes us take notice, like, ooh, that's unusual. Okay, that's kind of what we want to hear. Okay, so when I see that phrase, it means that the p-value is less than alpha. So in this case, that means that the p-value is less than 1%. So that p-value is low, which means our correct decision would be to reject the null hypothesis. Okay, that gives us evidence then that ha would be true. So as I look through my answer choices and I kind of skim through, I notice I've got two phrases, fail to reject and fail to reject, and then the other three say reject. So I want to cross off A and B because that is definitely the wrong decision based on the fact that we have a low p-value. Okay, now the other thing I need to do is read through and try to find one that says that ha is true. Now remember, our ha that we're testing is that the proportion of female college students minus the proportion of male college students is not equal to 0. Or maybe it was the other way around. Sorry, I can't remember now. But basically, we want to make sure that they are different. Okay, that they are different. That's what we're testing. Are they different? Not equal to. So if I skim through, it says there's convincing evidence that the proportion of all male college students who work for pay is the same. Okay, that's definitely not it. So that's like saying ho is true, which is the opposite of what we ever want to do. And then the other two, as I skim through, I see the phrase is different from, and I see the phrase is different from. Okay, so I need to take a closer look at these two. So I'm going to read them. Because the p-value is less than 1%, reject ho. There is convincing evidence that the proportion of all male college students in the study who worked for pay last summer is different from the proportion of all female college students in the study who worked for pay last summer. And E says, because the p-value is less than 1%, reject ho. There is convincing evidence that the proportion of all male college students who worked for pay last summer is different from the proportion of all female college students who worked for pay last summer. And these seem really similar. Okay, in fact, the only difference is this phrase in the study. So the first one, D, is referring to the males in the study, and the second one is just saying males, for example. So be careful on that, because the males in the study, we're talking about those 550 males. So that is not referring to the population. That's referring to the sample. The proportion of all male college students in the study, that is P hat M. Okay, whereas the proportion of all male students, that is PM. So in our conclusions, we always want to make sure that we are addressing, that we are concerned with making conclusions, making inferences about population parameters, or in an experiment about what would happen if we were to have more of this happening with a bigger group. What would we expect if we did this again? Would we expect those same results? Okay, so we want that one that's a population parameter. All right, so the third question says, what error could you be potentially making, type 1 or type 2? So remember, if you fail to, you might be making a type 2, but we're not failing to reject. We are rejecting the null hypothesis, which means if we reject, we might be making a type 1 error. So since we rejected the null hypothesis, we're possibly making that type 1 error if ho is true. If we reject something that's true, there's actually no difference in these two proportions, that would cause us to make a type 1 error. All right, so the next part of this are the 2 free response questions that are in the notes that follow. So these 2 free response questions here, if you will go to the next video, that it'll show you how to do these as well. So good luck.